Question 18, a railway engine is pushing a truck along horizontal rails at a constant velocity. As shown, the engine exerts a forward force. By the way, it says that the engine is pushing the truck, meaning it's moving in this direction. If the engine was pulling the truck, it would move in this direction. So this is the direction of its velocity. The engine exerts a forward force of 1.2 times 10 to the 5 newtons on the truck. The engine also exerts a net backwards force of 1.5 times 10 to the 5 newtons on the rails. Complete the free body force diagram to show all the forces acting on the engine. And it's a 4-mark question. So, and it's already given me weight and reaction force, which is a shame because those were the easy ones to do, right? So weight was acting down, therefore reaction force acting up. So the forces vertically are balanced. And now we need to consider the forces horizontally. Well, let's see. It says the engine exerts a forward force on the truck. So the engine's exerting a force of 1.2 times 10 to the 5 newtons on the truck. Therefore, the truck must exert the same force back on the engine from Newton's third law. For every action force, there's an equal and opposite reaction force. So because the engine's exerting this force on the truck is exerting the same force in the opposite direction on the engine. So there's 1.2 times 10 to the 5 newtons being exerted on the engine by the truck. It also says the engine's doing a lot here. The engine's also exerting a force on the rails. So let's draw that. So it's exerting a backwards force this time, and a backwards force on the rails. So the rails are experiencing a force of 1.5 times 10 to the 5 newtons. And because the engine's pushing the rails from Newton's third law, the rails has to now push back on the engine. So actually the rails is also applying a force. Maybe I should have used a different color. It shows a different Newton's third law pair. So therefore the rails exerts a force of 1.5 times 10 to the 5 newtons on the engine. So let's draw these forces out. So we got 1.5 times 10 to the 5 newtons. And by the way, we're going to have to label this force. This is the force. So this is the force of the rails on the engine. And I know there's also 1.2 times 10 to the 5 newtons being exerted on the engine. And this is the force of the truck on the engine. Okay, well, it does say that it's moving at constant velocity, right? Meaning the forces are balanced. So there has to be one more force to balance these two forces. And that's obviously going to be friction, right? Or air resistance or drag. Let's just call it drag. So you also have a drag force here. So that is your free body diagram. So yeah, you have to think about Newton's third law. Every time something exerts a force on something, that something else has to exert the same force back. Now it says, a student suggests that the weight and the normal reaction force form a Newton's third law pair. Explain why the student's suggestion is not correct. Your answer should include reference to the features of a Newton's third law pair of forces. I don't know why it's 5 marks, but let's have a go. So, okay, so it says your answer should include a reference to the features of a Newton's third law pair. So let's write down a Newton's third law pair. Okay, must, right? It must be a pair of forces. With equal magnitude for each pair. So each pair has the same magnitude. Oh, sorry, just write with equal magnitude. The forces must travel or must act in opposite directions. The forces must act in opposite directions. Those are the two that even the GCSE people know. Now let's talk about the other conditions, and that is they must act on separate objects, which we saw above. And then finally, they must be the same type of force. So now I'm going to go back to the question. I'm going to say weight and the normal reaction force do have the same magnitude and are acting in opposite direction. So far, so good. However, they are both acting on the engine. We're talking about the engine? No, just we're talking generally. However, they're both acting. So I'm just going to, they're both acting on the same object. And then number 5, which is they must be the same type of force. Also, weight is not the same type of force as the reaction, as weight is the force of gravity, right? Whereas the reaction force is a contact force. So when two things get really, really close to each other, like the hand and the wall, the protons repel each other, and this is like basically your reaction force. Don't need to know that, but this is not the same as gravity. It's a completely different type of force. So I think this will score us our 5 marks. Okay, a cyclist is moving up a slope at constant speed. The angle of the slope to the horizontal is 4 degrees as shown. As the cyclist pedals, there is a constant forward force acting on the cyclist of 150 newtons. The cyclist travels 215 meters along the slope. Show that the work done by the cyclist is about 30,000 joules. Okay, we need to know that work done is force times distance. I need to know that this force and distance, they must be parallel to each other. In this case, they are, right? The force is in the same direction as the distance you moved. So that means we could just substitute the values. Force is 150 times by the distance, which is 215 meters. What we get is 32250 joules, which obviously rounds to 3 times 10 to the 4 joules. Okay, it's a show that question, meaning we're going to have to use this work done somewhere in the next question. The cyclist must do work against the force of gravity and air resistance. Okay, so calculate the work done by the cyclist against air resistance. Well, what we can say is the work done by the cyclist. Okay, so the cyclist is doing work. He's applying a force and moving a distance. This is the work done we worked out in the previous question. So the work done by the cyclist is equal to the work done against air resistance, i.e. the energy transferred to gravitational potential energy, plus the work done. So let me repeat that. Is equal to the work done against air resistance, which is the energy transferred to the surroundings due to air resistance, plus the work done against gravity. This is the energy transferred to gravitational potential energy. So I'm going to repeat that one last time because I feel like I said that very awkwardly. So the work done by the cyclist is doing work, and this work, this energy is being transferred to two things. It's being transferred as work done against air resistance, and it's also being transferred as work done against gravity, so as gravitational potential energy. That's where his energy is going. So we know what the work done by the cyclist is. That's the work done in the previous question, which is 3 times 10 to the 4. Oh, sorry, I can't use the show that answer. Let's just say 32250, and that's equal to the work done against air resistance, which is what we're trying to work out. So WA plus the work done against gravitational potential energy, which is the energy transferred to gravitational potential energy, which is just mgh. So what we can say is plus mgh. Okay, the question is, what is mgh? What is the work done against gravity? Well, it's equal to his mass, which is 90 kilograms, times by g, which is 9.81, times by the height. Well, what is the height? How much height has he moved? Well, this is his height from the start to the finish. So we're trying to work out what h is. And as alluded to before, if you have a right angle triangle, where you know the angle and you know the hypotenuse, which is the case here. The side opposite the angle is the hypotenuse multiplied by sine the angle. And the remaining side is the hypotenuse multiplied by cosine the angle. So just looking at this, we have the hypotenuse, we have the angle. So the side opposite the angle is going to be the hypotenuse, which is 215, times by sine the angle, which is times by sine 4. So this is what the height is equal to. So multiplied by 215 sine 4. This is going to give me some answer. And then let's make the work done against air resistance the subject, which is work done against air resistance is 32250 minus MGH. Let's work out MGH. 90 times 9.81 times 215 sine 4, which I get 13241 joules. So minus 13241, we get, if I round to two significant figures, which is what I'm going to do, we get 1.9 times 10, 1, 2, 3, 4, times 10 to the 4 joules, because it's, energy, work. Okay. State one assumption that must be made when calculating the work done against air resistance. So when we calculated the work done against air resistance here, we assumed that all of the work done by the cyclist was converted to work done against air resistance and work done against gravity. However, in real life, maybe that's not the case. Maybe some of the work done by the cyclist is also converted to work done against frictional forces. So the friction between the tires and the ramp. So maybe some energy was transferred due to that. So the assumption made was there was no work done against frictional forces between cyclist and floor. Or a more general way to say that is the only two variables involved were work done against air resistance and work done against gravity. So we assumed those were the only two things involved. I prefer what I've written at the start. At the top of the slope, the road becomes horizontal. The cyclist continues to pedal with the same force. Explain how the speed of the cyclist changes as the road becomes horizontal. Well, as the road becomes horizontal, there is no longer work done against gravity, right? Because he's no longer going up. So there is no work done against gravity, right? So all of the work done is against air resistance now. Cyclist still, but he's still applying the same force. So cyclist still applied the same force. So his speed must increase. Because where did that extra work done go to now? It's going to be work done or energy transferred to kinetic energy. So work done by the cyclist is now going to kinetic energy instead of gravitational potential energy. So that's why he will speed up, because he no longer has to do work against gravity. So now he has some extra energy that could be converted into kinetic. So he's going to accelerate for a bit until the forces balance out once again, and then he reaches terminal velocity.